Hello class, I'll be lecturing on certain sections from chapter 3 in the Barron's book, which is Differentiation. And we're going to start with the derivative of an inverse. And so, in order to figure out the process of taking the derivative of an inverse, let's start with a graphical explanation of it. So here we have a function, f of x is equal to x squared plus 1. And that's graphed, represented by this curve here. And hopefully most of you remember that the inverse of a function is found by reflecting that function across the origin, which is this line here. And so, the inverse of f of x here would look something like this. And we'll call that g of x. Now, the kind of question that they're going to ask you about taking the derivatives of inverses is, given function f of x equals x squared plus 1, find the derivative of the inverse, which is g, at a certain point. And for our purposes, we are picking 2, 1. And so find the derivative of g at x equals 2. Alright, now in order to do this, we have to use function f of x, obviously, because we don't know anything about function g. All we know is that it's the inverse of function f. And so what you have to use here is an interesting property of inverses, which is that with inverses, the x and y coordinate of one function, all the x's and y's are reversed in its inverse. And so, if you have 2, 1 here, you know that on this graph, on the corresponding point, you're going to have 1, 2. And so that's right there. And so to find the derivative of g at 2, you're going to have to find the x-coordinate of the corresponding point on f. And I know I put that it's 1 right here, but you wouldn't know that right away. And so what you have to do is you have to say, well, since you have x is equal to 2 on g, then the corresponding point y will be equal to 2 on f. And so you set f of x equal to 2 is equal to x squared plus 1. And solving, you get x is equal to 1. And so there you have it. So you're going to use that point, 1, 2, to find the derivative of g at 2. And so what you do is, well, let me show you. Let me show you what the slopes will look like here. So, here, on f of x, at the point of interest, we have a slope that looks something like that. And you will see, sorry, not quite right. It looks about like that. And you'll see that it has a certain run and a certain rise. And then, on the slope of g of x at the point of interest, you'll see that it also has a certain run and a certain rise. And you'll notice that the run and rise are essentially reversed on the two graphs. On f of x, we've got this short run and this steep rise. and on g of x we've got this short rise and this steep run, and it just so happens that they are reciprocals of each other. And so, all you have to do to find the derivative of g at your point of interest is to find the derivative of f at the corresponding point of interest and take its reciprocal. So, f prime of x equals 2x, and f prime of the corresponding point 1 equals 2 times 1 equals 2. And so, g prime of 2 equals 1 over 2. And that's your answer. And that is the way that I would recommend. There's a formula for finding this, as I'm sure you all know, because I've been forced to memorize that formula and do it on the tests. But I've always found that confusing, and so, for that reason, I recommend finding all of your inverses using this method of thinking. Next up, we have the mean value theorem. And like the derivative of an inverse, we are going to demonstrate it graphically. So what the mean value theorem says is that if you have a function, and we're taking y equals x to the third here, and you bound it between 2 points, a and b, that the average slope between a and b, or the mean slope, hence mean value theorem, which looks a little something like this, more or less, that slope will be equal to the slope of the curve y equals x third at some point in between a and b. And the formula that represents the mean value theorem is as such. The derivative of the function at some point in between a and b, which is c, is equal to, and derivative is slope here, of course, equal to f of a minus f of b over b minus a. And that's just the average slope or secant line between a and b. And so really it's a very simple theorem, and basically what it's saying is, well, it's saying what I said it said, that there's a certain point on this curve, more than one or more points, that will have the same slope as the average slope. And so let's do it out for this. So we have f prime of c, so 3x squared is equal to f of a negative 1, no, f of a, yeah, negative 1 minus f of b, 1 over, sorry, that's supposed to be a minus b. Negative 1 minus 1 equals negative 2 over 2, negative 2 equals 1. And so the average slope is 1, and some point c or x on this curve will have a slope equal to 1. And so 3x squared, 3x squared equals 1, x squared equals 1 over 3, x is equal to square root of 1 over 3, and that is approximately 0.6, and lo and behold, at approximately 0.6 on the curve, x equals 0.6, here-ish, we have a slope equal to the average slope. That's the mean value theorem for you, ladies and gents. Alright, next we have L'Hopital's rule, which is a way of finding limits a little bit easier. And so, as I'm sure all of you know, because we've all done L'Hopital's rule, what it is basically is when you're taking a limit of something and you come out to an indeterminate form, like 0 over 0 or infinity over infinity, you can take the derivative of the top of the fraction and the derivative of the bottom of the fraction, which will simplify the limit and hopefully allow you to come out with an answer. And so, a quick demonstration, which you probably don't need, as such. Limit as x goes to 3 of x squared minus 9 over x minus 3. And when you plug it in, you get 9 minus 9 over 3 minus 3 equals 0 over 0. That's one of our indeterminate forms. And keep in mind, L'Hopital's rule only works if you get one of these two indeterminate forms when you initially plug in. If you don't get one of these two, there are certain cases where you're alright, but most of the time that means you can't use L'Hopital's. Anyway, we get 0 over 0 here, and so we can take the derivative of the top, the second here, take the derivative of the top, 2x, bottom, 1, and you get a nice clean 6. And that's your limit there. Now let's get to the tricky part of L'Hopital's rule, which involves when you have to change the function in order to come out to your desired indeterminate form. So, here we have limit as x goes to infinity of x sine 1 over x. And when you plug infinity in, you get infinity times sine of 0. That's infinity times 0. Not one of our indeterminate forms, as you can see. However, this right here can be shifted around to give you one of our indeterminate forms. And so the trick is to take the x and put it in the denominator. And so to do that, what you do is take the limit as x goes to infinity, the sine of 1 over x over 1 over x. And plugging in there, you get sine of 0 over 0 equals 0 over 0. That's one of our indeterminate forms, which means we can start using L'Hopital's rule. And using L'Hopital's rule here, well, I'm not going to show it to you, but just know that if you take the derivative of the top here, derivative of the bottom, you will eventually come out to the correct answer. Now, there's one other case that involves a slightly different trick. And for that last one, we had, just saying, we had infinity times 0. But that also works for infinity minus infinity. Also not one of our initial indeterminate forms, but if you happen to get infinity times infinity, you can do that same trick and work it so that you're allowed to use L'Hopital's rule. Now for this next trick, let's consider the function, the limit as x goes to 0 of 1 plus x to the 1 over x. Plugging in, we get 1 to the infinity. Not one of our indeterminates, but something can be done. And so, let's set y equal to 1 plus x to the 1 over x. And let's take the ln of y is equal to 1 over x ln 1 plus x. And so, we have the limit of the ln of y is equal to, the limit as x goes to 0 of the ln of y is equal to the limit as x goes to 0 of 1 over x ln 1 plus x. And plugging in, we get infinity, whoops, I did that wrong. Oh yeah, there we go. Ln of infinity is, or ln of 0, ln of 0 is 0. So plugging in, we get 0 over 0. That's an indeterminate. You can use L'Hopital's, but keep in mind, I'm not going to solve this one out either because it's kind of long and annoying, but keep in mind, since you're taking the limit of the ln y, you're eventually going to have to, you're going to get an answer where you have to use e to eliminate the ln part, and then you'll have your final answer. Anyway, you saw how this was 1 to the infinity. This also works for the semi-indeterminate forms of 0 to the 0, 1 to the infinity, which we have here, and infinity to the 0. So those tricks can be used for this, this, and this. Alright, so our last section is recognizing a limit as the definition of a derivative. And in order to do this, the most essential part is that, by the way, before I go into this is kind of a lame thing to do, and I figured probably not going to be on the test, but anyway, it's in the book, so I'm lecturing on it. Anyway, you have to go all the way back to when we learned the definition of a derivative, which is derivative at point C is equal to the limit as h goes to 0 of f of c plus h minus f of c over h. And so, you may be given a limit that looks something like this. The limit as h goes to 0 of 2 plus h to the 4th minus 2 to the 4th over h. And that looks surprisingly familiar to the definition of a derivative. And so you can say 2 seems to be kind of the thing here, so this is equal to the derivative of something at 2. And that's something, f of x, would seem to be equal to x to the 4th, because you've got powers to the 4th here. And so, all you really have to do is find f prime of x at 2, and that's going to be equal to 2. Sorry, why did I put x squared? I meant x to the 4th. 2 f prime of 2 is going to be equal to 4 times 2 to the 3rd is equal to 32. That's it, really. You just have to recognize that the limit is the same as the definition of the derivative, and figure out what your f of x is, take the derivative of it, and you're good.